Yeah, uh, today I decided to talk about what is usually called retarded time and overall how we model interactions if we have to talk to each other, as simple as that, or in more contextual sense, if there is one object interacting with the other, for example, a positive charge interacting with a negative charge, or a mass interacting with another mass, gravitationally speaking, in what way do they interact? So this can be called modeling interaction. So overall, we're going to talk about retarded time. In very simple sense, if I ask like light from Mars, if there was a radio signal that starts from Mars and it has to reach a person on Earth, how much is the time difference? It doesn't reach instantaneously. It takes about 15 minutes to 30 minutes or 45 minutes based on where Mars is. It could be on the same side of Earth, and then it is a smaller distance if it is on the opposite sides of the sun. Then you have more distance to travel. So the delay between the time a signal starts from the source and reaches the observer, that pretty much is the idea of retarded time. But this will play a more important role when we talk about interactions. So first of all, let me bring in the idea of uniform velocity and uniform acceleration in a simple context. Then I will talk about what if there was a maximum speed, how does that change, and then talk about interaction. So three things. I'll say first, the standard Newtonian. So in Newton's time, so uniform velocity. And uniform acceleration. And the same thing repeat in the context of Einstein's special relativity. Same. How do we see uniform velocity and uniform acceleration also? And that context we'll talk about proper acceleration. And third is interactions. Like terminologies like action at a distance, what does that mean and how things change in the modern way. So action at a distance and the modern way. So let's begin with Newtonian physics. So this is sort of a summary. So let's have a plot. We will do it graphically. So let's say that this is time and that's position. Notice that in introductory physics, we often have position on the y coordinate and time on the x coordinate, but it doesn't really matter later, especially in the Einstein's context. For some conventional reason, there is nothing wrong in doing either way. It is the time that is shown on the y-axis. Now, let's see how things look like here. If you're at rest, so you let's say this is your position. You might be somewhere. This could be the main street of your town, or a street on your town, and we're talking about everything along a straight line. Space is three-dimensional, but for simplicity, let's think of motion happening only along a line. So if we did not worry about time, you can go on this side, that side of the street, everything is happening along a street, let's say. You're sitting on at one point on the street, and if you keep sitting on the street, and if you switch on the time, then what you're saying is that this your position is like this. So this is your world line in a sense. So this is often called the world line. So you're sitting here at every point in time. So you take, say this is t equal to 0, t equal to 1 year at the same time, t equal to 2 year at the same time. So that's a simple position time graph. Often
you meant to say at a future time you are at the same position if you're sitting, right?
correct. Did I say it wrongly?
You said opposite, but that's okay. So the point is, like, even if you are sitting, you can represent it on a graph by this straight line that you're aging, but you are not changing your position.
Correct. So
Your location is fixed.
Yeah, time is changing. Here, time equal to, let's say, 1 second, 2 seconds, 3 seconds, but the position is the same, right? You're having the same position. Yeah. This is often in elementary or introductory physics courses. We say position time graph. That's what it's plot or graph. That's what you would call. You could have been sitting there before time t equal to 0. This is just a reference origin. Like you set your time t equal to 0 now. That means before time t is equal to 0 also you might have been sitting there, and that will be your plot like that. So that's a simple rest coordinate, right? That's a simplest graph you can have. So let me take this information off, and now let's talk about uniform velocity, right? So this is at rest. So this is at rest. So that's a qualitative picture of something at rest forever in a sense. So let's have another system. So we have again x, and this time we would like it to move, and let's say at time t equal to 0, it's at a point on the street that represents our world, if you want. So that's the street, everything happens along that street. You can go up and down, and let's say you start going to the right side of the street, right? So this represents that motion along the x-axis. Notice when I draw that line, what I mean is that I'm not interested in the time. That's a physical motion of that object. So I'm physically going with let's say I'm driving a car, I'm physically traveling on that street. If you were to take a movie, you will see that point moving towards your right, and you could be moving at 30 kilometers per hour. But if you want to see this in the position time graph, now the position is changing as time goes, right? So at t equal to 0, it's here. At t equal to 1 second, it might be here. So t is equal to 1 second is somewhere here, right? So it has moved, so it's down there. At t equal to 2 seconds, it's somewhere here, and so on, right? So that's your word line in this case. Notice I'm drawing two things. This is if you were to not have the time at all, then that's a physical motion of the object. So you just see it going to the right. But this is the actual word line or the position time graph, right? So that's the word line. When I try to see that with respect to time, that's what it is. It need not have started from rest here. It could have been, the car could have been coming from the left and then going all the way to the right. In that case, you say that's a straight line. So a straight line in the position time graph represents a uniform velocity. So everything is uniform. A simple situation. So that's uniform velocity. Of course, you could be traveling with uniform acceleration in the sense that you start from rest and then pick up speed. And that's also a normal motion that we come across. And that will look like. So that's position again, that's time. And let's say this time you really start from rest. So at rest means, so again, what you're doing is that physically speaking, you start from here and you start going in that direction. But this time you're speeding up in the sense that at zero time, your speed is 0. Then you pick up some speed in the first second, you pick up more velocity in the second, and so on. That means to say that if velocity is changing, your slope has to change. So this slope here means how fast it is going. If it was vertical, that means it is at rest. And as the slope decreases, if you want, with respect to this x-axis, it is going faster and faster. So it has to start with 0 slope because it is starting at rest, and then its slope has to increase. Right? That's a accelerating particle. So it is, notice again, the slope is 0. That means it is at rest, and it slowly increases. That means its velocity is keeping on increasing. I could have done the following feature, that instead of actually having something start from rest, we could have also talked about something that comes from the right side of the street, comes to a stop, and then goes back. Right? That will be something like falling from the sky. That is an acceleration towards the right, since while it is coming down here, it is decelerating, and while it is going back, it is accelerating. That will be a representation of, like, if I were to stand here and throwing a ball up there. So if that was the direction of the sky, then the ball goes up, reaches a maximum point, and then comes back and falls. So that's a visualization of how a stone being thrown up in the air goes up. So the acceleration, something is being pulled towards your right, goes up, stops there, and then comes back. And the position type graph, that would look like this. And this is a parable, right? So if I were to really write equations down for this, this is simply, so the first one would be simply x remains the same all throughout. So right, x just remains a constant. In this case, x would be equal to x naught plus vt. So then notice it is linear in time. By linear in time, I mean as time increases, x also increases in a linear sense. In equal times, it's equal distances that is traveling. On the other hand, when it is accelerating, this is equal to x naught plus half a t square, where a is the acceleration. Notice there is a t square there. That means for every second that you increase from, for example, for 1, if it is a quantity in x, for 2 it is 4, and for 3 it is 9. So it increases like 1, 4, 9, 25, and or 1, 4, 9, 16, 25, and so on. It's quadratic in time.
We are saying that it did not have any initial value.
Yes,
like initial
and
velocity.
I'm also saying that it started from initial velocity to be 0. So that's for simplicity. I'm assuming that in general it could have been having an initial velocity of some amount, but I want to do in the context that I'm talking about, it won't be necessary. That's for simplicity alone. Yes. So that's the three motions we can talk about, but notice one point here, as I sort of mentioned here and there, that the slope of this line or the curve here represents the how fast something is going. This is at rest, so if the speed is 0, it looks vertical, and more I bend, then I'm going faster. And in this case, when I say bend, at any point you have to draw a tangent, right? So that's what I mean by how fast it is going. So pick a point on the curve and think of a gradient if you want, that's what it's called, or draw a tangent, and how much it is sliding to the right, that means it's going faster. And then you can ask, how fast can this go? So you start from rest and you keep increasing your speed, it seems like it goes faster and faster. And as you go more and more to the right, it can increase as much as you want. So there is no bound on this velocity. So one conclusion here is that there is no bound on velocity, like at least in the way we have shown here.
But
And
this
that,
is Newtonian mechanics you're talking
correct,
right now.
we are talking about Newtonian physics here completely, right? There is no, this is a parabola, and there is no bound on the velocity in this. But that's not okay in terms of Einstein's theory, because Einstein tells us that there is a maximum speed available to us, and that's the speed of light. Nothing can go faster than that. So we have to change this a little bit. This remains the same idea, but we have to change this. The conclusion is different. It is not possible for a particle to go if you're going uniform with uniform acceleration, you cannot travel in this manner. In fact, uniform acceleration itself is redefined or restated as something going with proper acceleration. I won't go into details there, but the plot changes. There has to be a correction to this, and that is the following. So change the code. Okay, so now this is all Newtonian physics. Now we are doing Einstein's. This is called special relativity. And there the idea is that we have again x and t, and if something is at rest, it's the same idea. You will still go straight, and that's 0 velocity, right? If something is vertical, then it is going with 0 velocity, just stays at rest. This means this is a whirl line of a particle that stays at x equal to x naught, and it just stays at rest. That's a simple situation. Nothing, no difference between Newtonian physics and Einsteinian physics. Going with uniform velocity, now there is a slight difference, and that is that you cannot go faster than a certain speed, and that speed, if we pick to be the speed of light, and for convenience, often we pick that to be the 45-degree line, and that is typically the case when you're actually having the C here plotted. But for our purposes, we will say that there is a maximum speed. So this line represents the velocity or something moving with speed of light. What that means is that you cannot have a particle go beyond that. So this is allowed. So this is allowed, because the slope here is less than this, right? But you cannot have something go like this. If the same particle was going this way, that's not allowed because the slope is faster than speed of light, right? It is starting from x equal to x naught. Its slope has to be less than this dotted line. So this is not allowed. So let me erase that. So this is not allowed. So this is again a reference line here that is parallel to the speed of light. So this is something going slower than speed of light. Again, otherwise, except for the fact that there is a maximum line there, the equation and the curve looks pretty much the same, right? X is equal to x naught plus Vt. So x naught plus Vt. So that's a simple extension, except for the fact that there is a maximum slope there. Now let's come to uniform acceleration. And if we say that there is a maximum speed, clearly that is not that is in contradiction with the curve that we had shown here. So we have to modify this. And the modification is the following. So this time, that's your maximum speed possible. Let me draw it on both sides. And this time, you start from rest, let's say, and remember, just for reference, that's my Newtonian curve there, but that's not allowed because it's sloped very quickly. Like somewhere at this point, its slope is going at the speed of light, and after that point, it is going faster. So that's not allowed. Instead, what we have, so that's a parabola. Instead, we have hyperbolic curves. So what we have is a hyperbola, and it looks like this. And just to clarify how this works, notice that again, the particle itself is starting from here, physically speaking. It comes towards the origin, turns back, and goes back, right? That's what the particle is doing. So physically speaking, this is like throwing a stone up in the air. Acceleration is towards the right. So it is decelerating when it is going to the left, comes to a stop, and then instantly moves or falls down in a sense to the right. That's a physical diagram, and that's the world line. And as it goes farther and farther, its slope tries to approach the speed of light, but never becomes the speed of light. So in that sense, it is always away. What about the equations? The equation looks like x is equal to x naught times the square root of 1 plus, this is the equation of a hyperbola, and that is this speed of light c coming in. There is a times square and divided by x naught square. Let me write that as x naught square, where x naught itself is c square over the acceleration a. So I have made some simplicity here. I have chosen my initial point so that it is exactly, or it's related to the acceleration. So that's not necessary, but that's just so that this equation looks simpler. Notice the initial point, the initial position here, is related or inversely related to the acceleration. That's not at all necessary, but then this equation looks much simpler that way. One might wonder, always we say that in some extreme limit, we should always have the Newtonian physics coming, being accurate enough. So in what sense is that true? If I were to make an approximation that this numerator is very small compared to the denominator, I can expand this, but it's an approximation. So I will say that's an approximation, that's not equal, and that's equal to x naught plus, if I expand this as a series, like if you have, for example, a binomial expansion, a plus b the whole square, you can expand it. So similarly, a square root is basically a binomial expansion, can be used to expand that, and the power for this is half, so I get a half there, and basically this term, but the x naught cancels out, x naught is c square over a, so that simply gives you a times t squared. There are higher orders, which is the correction to this, but the higher orders correct itself in such a way that it will always make sure that the speed doesn't go faster than speed of light. So the basic message here is that in Newtonian physics, uniform acceleration is described by a parabola, and in Einsteinian physics, the uniform acceleration is described by a hyperbola, and that makes sure that things don't go faster than speed of light. So that's now we have motion described. Now let's talk about two objects moving, and we would like to talk about what is the retarded time between them, and is it possible for it not to see the presence of each other. So, or in other words, if there is a finite speed of light, one can ask the question that how far can we see the universe? For example, our universe has a finite age. It is not infinite. Our universe has an age of about 13.8 billion years. So that's the age. And in that amount of time, light has traveled a fixed distance, which means to say that we cannot see anything beyond that. So we have a limited view of our universe. Even if our universe was bigger than that, we will not have any sense of it, because no information in the form of light and anything has reached us, and we cannot feel or sense it. And that will be called the radius of the observable universe. Right? In that context, we can ask, is that possible that, okay, so that's the trivial sense that some light started from there and reached us. Is it possible that due to some dynamics, even though something is really close to us, we don't actually sense it because light can never reach from there? So is that possible to have a scenario? And I'm going to show you a scenario where an object could be very close to us, but still light cannot reach us because of the dynamics associated with the two objects. So, and that's a pretty simple extension of what I would have already told you, but let's see that. So first, let's have a simple situation. So that's our time and x. And this time, let's have two objects, right? So that's point A and that's point B. There are two friends sitting in their home, and their world lines represents this, right? They are both sitting in their respective homes. And that's how their world line looks like, right? Now, one of them sends a text message to A. Text messages are radio signals, or they go at speed of light. So they'll go the fastest way. So they go this way, right? So they're going, so it's pretty much 45 degrees. So they go this way. So at time t equal to 0, a message is sent by A, goes to B, and that's received here. And let's pretend that the friend B sends back that message instantly, or sort of reflects back, or the A tries to get the message that the message has been received, and immediately it comes back, right? That message comes back. And this is the time, let's say 0, that's your time t1, and that's your time t2. At time t equal to 0, a message is sent, it is received by B, and t2, the message comes back, right? That's an interaction, that's communication, right? And we want to ask, is there a scenario like this that you can never have a communication at all, even though they are sitting close to each other? And that's what I want to point out. And remember that interaction, like for example, if there are two galaxies or two planets that have to interact by gravity, they can interact only if they communicate like this. That's our understanding as of today, that they have to send a light. If it is a charged particle, they send light, and the light has to come back for interaction. If it is gravity, they have to send what is called gravitons. So maybe I should write that down. So if it is a charge, the particle that goes is photon. So this communication, this text message that we talk about, in the case of charge, is a photon. It has to go and come back. It travels at the speed of light. That's the idea of photon. And if it is gravity, so let's say if it is mass, then it is graviton. And remarkably, both have the same speed of light. Both travel with the speed of light. But now let's have a scenario, the following scenario, basically the same idea as we had done there. So we have this. And this time, have a particle go with uniform acceleration to the left, and then come to a stop and then goes back, right? That was the idea of uniform acceleration in Einstein special relativity. So that's your B, right? Your friend B is moving to the left with uniform acceleration, comes to a stop here, and then accelerates to the right. And friend A does the opposite. Right, that's two friends. Instead of sitting in their respective homes, they are traveling in cars. They start from very far away, come towards each other. They could be coming as close as they want, but they're on the two opposite sides of the origin, and then they go back. If we think of world lines, they will look like this. Right? Their curves will look like this. Correct. And the world line here, the curves will look like this. And now let's say we again ask the question that the friend A has to send a message to send B, and it has to go with speed of light, right? That's the only limitation, that it has to go with speed of light. That means to say that its slope cannot go beyond this 45 degrees. And you notice that you can pick any point you want on A. So that's your A. Let's say somewhere here, right? That's here. And you send a signal, light signal, and it never touches B. Right? You can go as early in or as behind in time as you want to, and a signal from A will never reach B. And the same thing from B, a signal from B will never reach A. Even though they come very close, you can make this come as close as they want, but the dynamics is in such a way that they will never know the existence of each other. Remember, if not for light, there is no sensation we have, and they will never know about the existence of each other. So you could have in our universe two such objects which come very close, but they will never know the existence of each other. So in that sense, a very non-trivial conclusion you make, but
so
yes.
So the point is, like, I think here you are drawing your x and t coordinate system in a certain way. But what decides then A and B are supposed to sit on the opposite sides of the origin?
I'm just choosing a very particular case. So this is a possible. So think of a universe. We are not saying that the whole universe, I'm not saying this universe cannot communicate with this universe. That's not what I'm saying. I'm just saying our universe is a straight line, correct? It could be three-dimensional also. I just had to extend that concept. But to begin with, they are on extreme two ends. They come very close, but they are accelerating. And that motion, for some reason, excludes A from interacting with B and B from interacting with A. Only those two particles. It doesn't mean that, for example,
suppose, let's say, what if I had assumed that the two, like that A and B are on the same side, let's say.
Then they will be able to communicate.
Yeah, so I guess the question would be, like, whose origin is this? Who is making the observation?
There is no observer. We are asking the question, can A interact with B? That's the question we are asking. And the statement is that they cannot interact ever if their motion is this, even though they come very close to each other. In that sense, it's non-trivial.
Well, I mean, I'm slightly, again, confused about this thing. When you're describing the motion of A here, like, what are you exactly telling? That it is going negative? Like,
no, it's not going negative. Okay, so this is, okay, again, I have a straight line. Okay, that's my world. And there are two objects here, very far away, let's say, and they decide to come towards each other, but not in any way they want to. They are decelerating while they are coming towards each other, right? They are having an acceleration. It doesn't have to be the same acceleration they're decelerating with. They're decelerating and then they come close, very close though, and then they go back. And the same thing is done by this person. And you would think, very naively speaking, that, oh, I'm coming towards it. You're pointing towards each other, right? Yeah, it's like saying two cars come towards each other on the road. Come on, then if I shine a light, light is going to be faster than me. So the light should reach the other person. But the way I have constructed is such a way that before the light reaches, I'm going to go back. Like, I'm going to return back. And it's just a special scenario. It doesn't mean that every object on the right side cannot speak to each other. That's not what I'm trying to say. That's not the case at all. But if you have such a very special motion, And it's possible. At least there is one situation where that can happen, and that's non-trivial enough. Right? That's you don't expect that to happen, naively speaking. Does that convey the point?
Yeah, it's very non-trivial, I would say.
Yeah, yeah. But you accept, right?
Like, I think the point is like the moment you draw your cone, it gets decided by some origin, and where is that origin sitting changes things. Like, I mean, whose origin like is that? Like, I mean, always a coordinate system is associated with someone.
Okay, put that here. That's your cone. Doesn't matter. Right? Will not matter.
Yeah, but now can you draw your hyperbola for those two?
Right here, that's your hyperbola. Right. Hyperbola is like this, right? And maybe
yeah, but you again created that.
Right, it's instantaneously it's down here, right?
Okay, is there an example?
Example. That's the example, no?
Like, is there a physical example that you can point to?
I thought this was physical, but you mean is there a galaxy which is doing this really? And but then we will never know, right?
I need, like, for example, like these do matter, what speed you're moving with and all that.
Oh,
like,
that is x equal to like just the same equation, right? You can take the same acceleration.
No, I'm not worried about that, but I'm just like literally thinking about a problem that can describe it, describe this kind of scenario. A physical situation that can actually describe this kind of scenario. Like, you are basically saying that one particle is invisible to another one.
Or maybe your point is that, is it, suppose we are the observer, right? Let's say there's a third person C, right? So let's say we are standing somewhere here, right? I will always be able to see this particle from here, correct? So C comes from here. So that's the light coming from a galaxy far away, right? So I'm sitting here. There is a galaxy, some motion, light comes and hits here. But then the light from A probably will never come and hit me. Yeah. So I'm saying there are regions of space out there which probably we will not ever be able to get information from. Maybe that's what. So I think the point is, if there is we talk about observable universe and then say that, oh, it is because we have a finite age for our universe, which is 13.8 billion years. And that's the reason why we are not seeing the whole universe. But here I'm saying, even if we were to live forever, there will be regions of space because of the motion of the particles that we will never be able to see.
So another question, like the way I used to learn, understand the cone, like that world cone, is that the reasons you're describing regions, they are considered. So bottom of the cone is past, the top of the cone is future, and the regions on the side of the cone were considered the present. And in present, you cannot communicate with another side of the present, which is kind of looking like that you cannot communicate with the other side of the present. But in future, Like, I mean, as the things grow, they will be able to intersect their world lines or
Yeah,
world.
that is, I think the way you're looking at that is probably here. So this is the scenario that usually we consider. So for example, if one was, so let's say one was accelerating, and then if you're at rest, right?
No, even no, even
You can be on
otherwise.
that side, it doesn't matter. Like usually, always you want to put your cone here. This is not the cone, that's just all I mean, for instruction, we always draw the cone here. It's always the instant that you're interested in.
Yeah, exactly. Yeah, I agree.
Yeah, so you want to draw the cone wherever you want to. But now at this way of looking at it, if there was an object at rest, right? This is your friend A, and that's your friend B. Now, if you notice, friend A will always be able to communicate, right? So here you have, and light goes in, it will intersect, right? It will always be able to communicate. So it is not that it is because it's on the left side or anything like that. It's just the motion that is, it's a dynamics that is making it not being able to talk. It is not because where you're sitting in the universe, it is the motion, right? It is in such a way that light is able to escape it. But that's very special. It's a very, we will be missing only very little part of the drama in the universe, not the whole, everything in that region. So we're not excluding a region, it's just that object that is moving there that we'll be missing, if that helps.
It's slightly, yeah. I mean, maybe we can discuss it again later.
Yeah, sort of.
So did you have like, I mean, were you going to discuss this further in some context?
Yeah, that's all. Basically, that's my point, that this is the infinite retarded time, right? So the retardation between this to the point where you receive it, right? If your observer is here and your source is here, the retardation is infinity in that sense. So that was my, so that I didn't get a better title. I should have been more creative, but the idea is that they are not able to interact. So I should have used some observable universe or something like that, looking back. But everything would have its own non-triviality in a sense. So my idea was just to show this very counterintuitive conclusion.
Yeah, it is. Yeah.
Yeah.
It is counterintuitive, yes.
Yeah. And that's all. I don't have anything else. A short talk, but I think.
No, it is interesting because I didn't think it in this fashion. I used to think that, okay, like the present cannot talk right now. It's like the same thing that you're calling a friend, but the friend is hearing it in the future, right?
Yeah.
So because of the finite speed of light, I mean, the signal will reach him, but it will reach him in the future. So the way I used to think is that, oh, they have their own world cones, but somewhere in the future, their world cones are going to interact, like intersect, intersect. And that will make the, like, that's where they will talk to each other. So it might be like somebody is from the past is talking to you right now, which is happening at every instant, basically.
Yeah.
Like the moment I am telling, it is already a lag of a second before you can hear it. So you're already in the future. I am in my signal generated in the past.
Yeah, or more dramatically, the stars that we see are a billion-year-old.
Yeah.
Right?
So so exactly, like the closest star is 4 light years away, means that light, when we see it in the sky, it is the 4 year ago that light started from there.
Yeah, we are looking in the past. but
So we are looking in the past. So
but
that's
there
the
the
way I
point
used
is,
to think.
yeah, the non-triviality there is we always associate the time because it is so much far away in the past. There is a delay in there, but I'm saying you could be very close, but the
And still
galaxy
you
is
cannot see
moving.
it.
But the galaxy is moving in such a way that we will never see the signal. So that's the counterintuitive feature here.
So in that context, did you ever like try to relate it with dark matter, or like?
No, I didn't.
Mhm.
I didn't connect this with that at all. I have not thought about that at all. Good point. Yeah. So you're saying,
Like you are saying, we are not able to see something, right? And this is a situation in which you won't be able to see something.
but then it won't be able to interact either. If you can't see something, you won't interact either.
But
So,
are we interacting? We are not interacting with that. Dark matter is dark because we are not interacting.
but gravitationally it pulls, right?
Yeah,
The effect
yeah,
is,
yeah, yeah, yeah. Yeah,
effect
you're
is,
right. You're right. You're right. You're right.
So, and if the effect is there, that means it is interacting. It's just that we are not sensing it. Yeah, but I don't know that yet. I have not thought about dark matter in this context. Yeah.
Interesting. Yeah, I think this is a good talk. Yeah.
Okay. Nice.
Very interesting point.
Jovan, any questions? Was it
No, sir.
okay? Okay. So maybe I'll stop here, or at least stop the recording.